Chapter 5, Weak Typicality. In this chapter, we address the following issue. For a random vector x equals x1, x2 up to xn, where xi are IID with distribution px, what would be a typical outcome of the random vector x? We are going to see how typical sequences are related to data compression. Specifically, we will take a second look at data compression. Namely, we will discuss Shannon's source coding theorem. Section 5.1, the weak asymptotic equipartition property, or simply the weak AEP. Let us now introduce the notion of typical sequences. Consider tossing a fair coin n times. If the outcome is head for approximately half of the time, the sequence of the outcome is quote-unquote normal or typical. So the question is how to measure the typicality of a sequence with respect to the generic distribution of an IID process. There are two commonly used such measures in information theory, namely weak typicality and strong typicality. The main theorems are the weak and strong asymptotic equipartition property, or AEP, which are consequences of the weak law of large numbers. In this chapter, we will discuss weak typicality. Consider a discrete time random process x sub k greater than or equal to 1, where xk are IID with generic distribution px. Let x denote the generic random variable with entropy hx being finite. Let both x be the random vector x1, x2 up to xn. Because the random variables are IID, we have p of the random vector x equals p of x1 times p of x2 all the way to p of xn. Now here we assume that the alphabet x may be countably infinite. Let the base of the logarithm be 2, that is, h of x is in bits. Theorem 5.1 is the first version of the weak asymptotic equipartition property, which says that the following three equivalent statements hold. First, minus 1 over n times log of the probability of the random vector x tends to entropy of x in probability as n tends to infinity. This means that for any epsilon greater than 0, limit n goes to infinity, the probability that the absolute value of minus 1 over n log p of the random vector x minus entropy of x greater than epsilon is equal to 0. Another way to say the same is that for any epsilon greater than 0, for n sufficiently large, the probability of the absolute value of minus 1 over n log p of x minus entropy of x is less than or equal to epsilon is greater than 1 minus epsilon. The proof of weak AEP1 depends on the weak law of large numbers, which says that for IID random variables y1, y2, so on and so forth, with generic random variable y, 1 over n times summation k equals 1 up to n y sub k, that is, the average of y1, y2 up to yn, tends to the expectation of y as n tends to infinity. Here is the proof of weak AEP1. Since x1, x2 up to xn are IID, we have p of the random vector x equals px1 times px2 all the way to pxn. Then minus 1 over n times log of p of the random vector x is equal to minus 1 over n times log of px1 times px2 all the way to pxn, which is minus 1 over n summation k equals 1 up to n log of pxk, because the log of a product is equal to the summation of the logs. Now the random variables log pxk are also IID. Now by the weak law of large numbers, the expression in equation 1 tends to minus the expectation of log of px, which is equal to the entropy of x. And this convergence is in probability, and that proves the theorem. We now define the weakly typical set, which has two parameters, n, a positive integer, and epsilon, a small positive quantity. For clarity, we mark all n's in blue and all epsilons in red. The weakly typical set W sub x epsilon sub n with respect to px, a distribution on the alphabet script x, is the set of sequences small x equals x1, x2 up to xn in the set script x to the power n, such that the absolute value of minus 1 over n log px minus entropy of x is less than or equal to epsilon. Or equivalently, minus 1 over n log px is between entropy of x minus epsilon and entropy of x plus epsilon. The sequences in the typical set are called weakly epsilon typical sequences. In other words, to test whether a sequence is epsilon typical, we take the log of the probability of that sequence and multiply it by minus 1 over n. If it is close to the entropy of x within the margin epsilon, then the sequence is weakly epsilon typical. We now define the empirical entropy of a sequence x as minus 1 over n log of p of x. Now px is equal to the product of p of x sub k equals 1 up to n, because the random variables are IID, and log of the product of p of x sub k is equal to the summation of the log of the p sub k's. And the expression can be further written as 1 over n times summation k equals 1 up to n minus the log of p of x sub k. In other words, the empirical entropy is equal to the average of the minus log of p of x sub k's. With this definition, we can say that the empirical entropy of a weakly typical sequence is close to the true entropy Hx. Let us now take another look at definition 5.2. Theorem 5.2 is the second version of a weak AEP, which says that the following hold for any epsilon greater than 0. First, if a sequence X is weakly epsilon typical, then the probability of the sequence is lower bounded by 2 to the power minus n times entropy of X plus epsilon, and upper bounded by 2 to the power minus n times entropy of X minus epsilon. Second, for n sufficiently large, the probability that the random sequence X being weakly epsilon typical is greater than 1 minus epsilon. Third, for n sufficiently large, the size of the weakly epsilon typical set is lower bounded by 1 minus epsilon times 2 to the power n times entropy of X minus epsilon, and is upper bounded by 2 to the power n times entropy of x plus epsilon. Here is the proof of weak AEP2. From definition 5.2, for a weakly epsilon typical sequence x, we have minus 1 over n times log of px is lower bounded by entropy of x minus epsilon and upper bounded by entropy of x plus epsilon. By multiplying n, we have minus log px is lower bounded by n times entropy of x minus epsilon and upper bounded by n times entropy of x plus epsilon. Multiplying by minus 1 and so changing the direction of the inequalities, we have log of px lower bounded by minus n times entropy of x plus epsilon and upper bounded by minus n times entropy of x minus epsilon. This is equivalent to property 1. Second, property 2 is equivalent to theorem 5.1 because by definition, the events that the random sequence x being weakly epsilon typical is equivalent to the events that the empirical entropy of the random sequence x is close to the entropy hx. Now to prove property 3, we use the lower bound in 1 to obtain that the probability of the weakly typical set is lower bounded by the size of the typical set times 2 to the power minus n times entropy of x plus epsilon, which is the lower bound on the probability of a weakly typical set. Now, because the probability of the weakly typical set is always less than or equal to 1, we obtain the size of the typical set times 2 to the power minus n times entropy of x plus epsilon is less than or equal to 1, which implies the size of the weakly typical set is less than or equal to 2 to the power n times entropy of x plus epsilon. Note that this upper bound holds for any n greater than or equal to 1. On the other hand, using the upper bound in 1, we obtain that the probability of the weakly typical set is upper bounded by the size of the typical set times 2 to the power minus n times entropy of x minus epsilon, which is the upper bound on the probability of a weakly typical sequence. Using property 2, we have the probability of the weakly typical set greater than or equal to 1 minus epsilon. So we obtain 1 minus epsilon less than or equal to the size of the typical set times 2 to the power minus n times entropy of x minus epsilon. Therefore, we obtain the size of the typical set greater than or equal to 1 minus epsilon times 2 to the power n times entropy of x minus epsilon. Now combining 2, the upper bound on the size of the typical set, and 3, the lower bound on the size of the typical set, we obtain property 3. The theorem is proved. Basically, the weak AEP says that for large n, the probability of occurrence of the sequence drawn is close to 2 to the power minus n times entropy of x with very high probability. Second, the total number of weakly typical sequences is approximately equal to 2 to the power n times entropy of x. However, the weak AEP does not say that most of the sequences in script x to the power n, that is the set of all possible sequences, are weakly typical. It also does not say that the most likely sequence is weakly typical. To illustrate these ideas, let us look at a simple example. Consider a binary random variable x such that the probability of 0 is equal to 0.2 and the probability of 1 is equal to 0.8. With x being the generic random variable, the most likely sequence of length n is the all 1 sequence with probability equal to 0.8 to the power n. Now the empirical entropy of the all 1 sequence is equal to minus 1 over n times log of the probability of the sequence, which is equal to minus 1 over n times log of 0.8 to the power n. This is equal to minus log 0.8, and this is not close to the entropy of x. And therefore, the all 1 sequence is not weakly typical. This seems to be a contradiction because on the one hand, the probability of the weakly typical set is approximately equal to 1, but all 1 sequence, which is the most likely sequence, is not in the typical set. However, there is actually no contradiction because as n tends to infinity, the probability of the all 1 sequence tends to 0. Therefore, the weakly typical set, though does not contain the all 1 sequence, can still have probability approaching 1 as n tends to infinity. The interpretation of the weak AEP is the following. One can almost think of the sequence x as being obtained by choosing a sequence from the weakly typical set according to the uniform distribution. Specifically, the size of the typical set is approximately equal to 2 to the power n times entropy of x. If the entropy of x is strictly less than log of the size of the alphabet, which is usually the case, then 2 to the power n times entropy of x would be much smaller than 2 to the power n times the log of the size of the alphabet, which is equal to 2 to the power log of the size of the alphabet to the power n, which is equal to the size of the set of all possible sequences. Therefore, the size of the typical set would be much smaller than the size of the set of all possible sequences. By the weak AEP, we also have that the probability of the typical set is approximately equal to 1. For a typical sequence, the probability is approximately equal to 2 to the power minus n times the entropy of x. And so, the conditional distribution on a typical set is almost uniform.